Welcome back to COMP526. We'll start a new unit today on machines and models, which will be about representing mathematically what we mean when we talk about algorithms and data structures and their performance. My goal for you from this unit is to take some fundamental understanding that goes a bit beyond just what you do for programming. I want you to understand what the difference is between an analysis and running time. Then the important notions that we have for modeling different parts of what we do in algorithms. We have models for the input, we have models for the machines, and we have models for the cost of an algorithm for an execution. And we'll touch on the main notion that people use in computer science for expressing running time statements, the asymptotic notation. Again, some of these things you will have seen in previous modules if you've done an undergrad in computer science, and some are also maybe used even outside of computer science now, but we'll go from first principles at a faster pace than you would do this in an undergrad course. But everything you need to know for this module is in there. It's just coming at a relatively quick succession. So this module is about algorithms, so we should have a little conversation what an algorithm is. What I'll give you is a definition that still has some vagueness in it. So for us, an algorithm is basically a sequence of instructions, and you can say the metaphor is a cooking recipe. So it should tell you at each point in time what to do. Now, the difference to a recipe is, as you may know, if you're a hobby cook, sometimes the instructions are not so clear. At least if you're not an expert cook, there may be some steps that are not self-explanatory. That's something we'll have to avoid for algorithms. Algorithms have to be explained in a simple language that's understandable even for stupid computers that have no common sense and no experience. So they will be expressed in some formal language. So what we mean by this is it has to be mechanically executable. And for example, that can be a Python program or any other programming language. And we would distinguish this probably from a natural language description that maybe some large language model can translate to some code. But in this case, we don't have any guarantees that it does the right thing. We just hope it does something sensible. For an algorithm, we want precise instructions. A more subtle point is it should be a finite description. You have to be able to write it down. It's maybe obvious to state, but if you explain an algorithm on an abstract level, it sometimes is natural to specify things that if you spell them out for a computer, it would need an infinite number of cases, and that's not allowed. And then the last bit is to distinguish an algorithm from a concrete program. Not every program is an algorithm, and that's the vague bit. We want algorithms to solve an entire problem or entire class of problems, as opposed to just computing a specific thing. So maybe in terms of this example, if you're just computing the sum of two numbers, that would be just some program. If you have a method that computes the sum of any two numbers, that's an algorithm. Of course, that's a very simple program, and we'll look at a few more interesting problems, but that's the gist of it. We'll usually abstract it like this, as you will have seen. So there's some input going into the algorithm, then it does something, and it produces some output. That's usually our model for thinking of these. Of course, output could mean it modifies a piece of memory that you provided it with. That's also fine. And to illustrate this, an example of an algorithm could be the famous bubble sort that we all know is not such a great sorting algorithm. It's not so fast, but it is an algorithm. And it describes an idea that roughly tells you how to sort. But it's not a specific program. When you say bubble sort, there's many different ways how you can implement it. It depends on the programming language, how it looks in detail. And there's slight variations in bubble sort. I don't want to get too much into this if you haven't seen it in detail, but If you do bubble sort, you continuously exchange two neighboring elements if they're out of order, and you do this from left to right until you're one pass through the data. And then you do it over again. Now, one version of bubble sort, just cook until done. Do this until you've never made any exchanges. So you do one more pass over the data where you don't do any exchange, and then you know you're done. Another option is to say, I don't want to do anything with checking. I'll just do n passes, and I know n passes are enough if n is the input. That's two slightly different variations, but both would be called bubble sort. It's just the difference is too small. So you would call it both bubble sort, but of course the programs look slightly different. So an algorithm for us often is a bit more abstract. It's the key essence of a recipe for computation. And I understand this is a bit of a vague point, but hopefully you will see many examples in the course, and then we'll recognize which ones are coherent abstractions that might deserve a name. So much for algorithms. Don't want to lose track of Slido. The second part we'll be concerned with in this module are data structures. They're often called hand-in-hand algorithms and data structures, and that's for the following reason, that they're very related. A data structure is two things. First of all, it's some way of representing a piece of data in computer memory. And what is data? That depends, and we'll see more examples in the next unit. So I'll leave it a bit abstract here. But it's one, it tells you exactly, a data structure tells you exactly how to represent the data you're storing in computer memory in bits and bytes. And the second part is it has algorithms that tell you how to do something with the data in the representation that you have it. And usually we distinguish, it's either something queries, just ask a question about the data and updates change it, but you can have various mixtures. And an example you may have seen if you've done, that you must have seen if you've done in CS undergrad, is a binary search tree. But we'll see other examples. So much for the broad introduction. In the next section, we want to look a little bit about the specific analysis. So that's where the mathematical modeling comes in again. So far, it's been a bit wishy-washy and vague, and the terms algorithms and data structures need to be a bit vague. But what's coming here is trying to make things very precise. The whole motivation why we do this comes from the fact that if you have a certain algorithmic problem, there are usually many ways to solve it. And the question is which algorithm or which data structure is best suited. So you need a way to tell good algorithms or data structures from others, not so good ones. And I claimed bubble sort is not good, so I should have some way to quantify that. Usually we mean fast, but we might also mean space usage. Depending on the circumstances, one or the other is more important. We'll briefly look into parallel algorithms where time is again a bit more complicated, but we'll come back to that later. So what is algorithm analysis? It's a methodology that allows you to compare algorithms by measuring how well they work, and also to predict how fast they are. And how accurate that is possible depends a bit on what you define next as the model. But that's the goal. We want a way to compare different algorithms so that we can quantify their cost and find the one that has the better trade-off for us. And if we pick a specific algorithm, it's useful to be able to do at least a back-of-the-envelope calculation how fast it will be or how much memory it will take. That's the feasibility check. Now, one option to analyze algorithms would be implement them and just run them and see what happens. And sometimes that's the only option you have, or it's the fastest way to go. That can be possible. The problem with that is that it is a bit limited in what you can make as statements. you can run things on a concrete computer and you will get numbers for that concrete computer, but it's not clear if you can do if you can make predictions for other machines. Also, you have to run it on some concrete input, some data, and it's not clear if what you find generalizes to other kinds of scenarios. And lastly, you have to implement it. So if you think back when I said an algorithm is more of the essential idea of some computational recipe. If you decide you implement bubble sort one way, and that turns out to be bad, you never quite know if there's maybe a slightly better way to implement it that would do much better. And that's not so satisfying. So in particular, remember I had this comic about the philosophy of the module. We're after the universal truths of algorithmics. And all of this sounds like not so universal. So instead, what we like to do is have some way of comparing algorithms that survives the current hardware so that it can make statements that are a bit more eternal universal. We'll still have a model of reality that we might need to validate. Okay. Is that okay? Still works. I feel I was a bit too loud earlier. Is it okay now? Okay. I'm not. Okay. Aha. Right. So I hope the plug is in now again. Interesting. Is the volume okay so, or like this, or too loud, too low? You can hear fine in the first row, but the guys in the back have to tell me. Looks good? All right. Okay, sorry for that. So what this is all about is that we need a precise model to be able to do that. If we just rely on the current computers that we have, we'll only be able to say something about those. And so we need to abstract from the concrete machines we have if we want a statement that transpires beyond the current machines. Is maybe self-evident. And we'll come to how to model machines. What we'll also need is a model for the data we work on. Because again, we can try to run it on concrete inputs, but we often want something that is more generic. And there are three different models that people have used in algorithm analysis a lot. And you'll be familiar with those, or it's very intuitive. The worst case performance means take the worst possible input. And that's a bit pessimistic, but if you have a guarantee that your algorithm in the worst case is good enough, it'll be good enough in any case. Best case means take an optimistic point of view, take the best. That's usually just useful to rule out algorithms. If already the best case is poor, then maybe it's not worthwhile exploring that algorithm. An average case tries to interpolate between the extremes, and we'll come back to that in the context of sorting. So here you're just assuming there's some random distribution over inputs, and you're computing an expected value of the cost. Now these sound like you take all possible inputs and take the worst of them. Usually that's not well defined because we allow an infinite number of inputs. If the algorithm is for an abstract problem like add two numbers, the two numbers could be arbitrarily big. And it's unreasonable to expect that the cost of an algorithm does not depend on how big the input is. So instead we'll group inputs by the same size. All inputs of size n are one group, and then all these measures above pick from just a fixed size. So worst case would be the worst possible input with a given size, or the best possible input of a given size. So for each of these three different data models, we would get a function of n for the performance. It's not just a single number, it's a function that tells you for each input size how long would the algorithm take.